In the final video for this section, we'll look at another property of power series that will help us solve differential equations using power series. So if we're given two power series that are centered at x naught, namely f of x equals the summation from n equals 0 to infinity of a sub n times x minus x naught to the power n, and g of x equals the summation from n equals 0 to infinity of b sub n times x minus x naught to the power n, and both have a non-zero radius of convergence, we can then obtain the sum by termwise addition. So f of x plus g of x then has a power series that is equal to the summation from n equals 0 to infinity, and then centered at x minus x naught, and then all we have to do is we have to add the coefficients for the two functions. So we have a sub n plus b sub n times x minus x naught to the power n. Now, this type of addition only works if when you compare the powers in the power series that they both have the same power. So they're both to the power n. Now, if that is not the case, so for instance, if one of the powers is n plus 1 and another is n minus 1, what we can do to add those power series is we can shift the summation index. So I'll show an example of this. So express the series summation from n equals 2 to infinity of n times n minus 1 times a sub n times x to the power n minus 2 as a series where the generic term is x to the power k instead of x to the power n minus 2. So we have some freedom in defining what the power of each term is. So in order to do that, what we're basically doing here is we're replacing, so we replace n minus 2 by k. So what we can conclude from that is that n minus 2 equals k, or equivalently, when you solve that for n, that n is k plus 2. So anywhere you see n, you can replace that by k plus 2, and anywhere you see n minus 2, you can replace that by k. So let's start out with our series. So we have our series n equals to infinity of n times n minus 1 times a sub n times x to the power n minus 2. So now I'm going to replace n by k plus 2. So now I have k plus 2 equals 2 to infinity, and then my n here, I'm going to replace that by k plus 2, and then times n, I'm going to replace that by k plus 2, and then I have minus 1, and then I have a sub n, and that n I'm going to replace by k plus 2, and then x to the power n minus 2, and I can replace that by k. Okay, so now all I need to do is I need to simplify this. So for the bottom here, I can subtract 2 on both sides. And so my summation, instead of starting at 2, my summation will now start at k equals 0. And it will still go to infinity. And then I have k plus 2. I need to put parentheses around that. So I have k plus 2 times k plus 2 minus 1. So that will just be k plus 1. And then a sub k plus 2 times x to the power k. And that is my new summation, or my new power series that is centered at, or with the general term being x to the power k. Okay, finally, we'll show how an identity for a power series leads to a relationship between the coefficients of the power series involved. So the identity that is given is summation from n equals 1 to infinity of n times a sub n minus 1 times x to the power n minus 1, and then plus the summation from n equals 2 to infinity of b sub n times x to the power n plus 1 equals 0. And we want to show that this implies that a naught equals a1 equals a2 all equal to 0, and a sub n equals negative b sub n minus 1 over n plus 3 when n is greater than 3. So in order to combine these two summations, or these power series, what we need to do is we need to make sure that x has the same power. So for the first power series, what I want to do is I want to call n minus 1 equal to k. And so that means that k, or that n, equals k plus 1, right? So n minus 1, I want to change that into a k. And for the other power series, I want to replace n plus 1 by k. And so that means n plus 1 equals k, or n equals k minus 1. So now our first summation will be, instead of n equals 1, it will be k plus 1 equals 1 to infinity, and then n gets replaced by k plus 1. So we have k plus 1 times a sub n minus 1. That becomes a, and then k plus 1 plus 1, or if you wanted to, you could also directly replace n minus 1 by k, but I'll just show it here that if you just replace n by k plus 1 everywhere, you get the same thing. Sorry, that's minus 1. And then you'll end up with a sub k here. And then the way we replace that, we get x to the power k. And then for the second summation, it's the sum from n equals 2, but n here is k minus 1. So what we get there is k minus 1 equals one to infinity, and then b sub n. Well, n is k minus 1, so we'll replace that by k minus 1, and then x to the power k. And that is still equal to 0. So now let's simplify that. Right, so our first summation becomes k equals 0 to infinity. And then we have k plus 1 times a sub k times x to the power k, and then plus summation k equals 3 to infinity of b k minus 1 times x to the power k, and that equals 0. Now, we're almost to the point where we can combine these two series, but another thing that we notice here is that for this example here where f and g are given, both summations start at 0. So what we can do is we can write out the first 3 terms of this series. So we're going to manually get k equals 0, k equals 1, k equals 2. And so then we can start at k equals 3. So if we plug in k equals 0, we get 0 plus 1 times a 0. So the first term is a naught. Then the second term is when k equals 1, this becomes a 2, and then this is 2 times a 1 times x. So 2a1 times x. And then when k equals 2, we get 3 times a2 times x squared. So again, this is the first series where k equals 0, k equals 1, and k equals 2. So we can then add in the rest of the series, and that one starts at k equals 3 because we took care of k is 0, 1, and 2 to infinity of k plus 1 times ak x to the power k plus summation of k equals 3 to infinity of bk minus 1 times x to the power k, and that equals 0. Now, this identity holds for any k. So if this is true for any k, that means that, or for any x, that means that a naught has to equal a1 has to equal a2 has to equal 0. Because otherwise this cannot be 0 for all x. So all of these three coefficients have to equal 0. Now for the next part, we can now combine these two power series, and what we get is the summation from k equals 3 to infinity, and then our combined power series is k plus 1 times a sub k plus b sub k minus 1 times xk, and that equals 0. And because all of this is 0, it must follow that these coefficients have to be equal to 0 for all k's greater than or equal to 3. So we have k plus 1 times a sub k plus b sub k minus 1 equals 0. And this is for all k greater than or equal to 3. And we can then solve this for a k, and we see that a sub k is equal to minus b sub k minus 1 over k plus 1 for all k greater than or equal to 3. And that's exactly what we needed to show, right? A sub n equals negative b sub n minus 1 over n plus 1 for n greater than 3. Well, that's exactly what we have here. The only thing is that n is replaced by k. So those are the two things that we needed to show and that we have shown. So that completes this example.